when we are going for, we will discuss the topic Z transforms in our today's lecture. Z transforms is similar to Laplace transforms. Transform is similar to Laplace transforms for continuous time signals, used for continuous time signals or functions, and Z transforms or Z transforms are used for discrete time systems or signals. Right, they give us similar results. When you are going for Laplace transform, you are getting a continuous time output. When you are going for Z transform, you are getting a result which is continuous time signals. Here these Laplace transforms are utilized for differential equations, and here you will be utilizing this Z transforms for difference equations. You will be using this for difference equations. Now Laplace transforms are much easier for us when you are going for continuous time signals or systems, because they can be used for any single input single output systems. They can be used for linear time invariant systems. Similarly, Z transforms can be used for discrete time systems with difference equations. Therefore, let us see what is the Z transform and what are the relationship between Z transforms and Laplace transforms. Let us first try and define what is a Z transform. What is a Z transform? Z transforms can be applied on continuous time systems, x of t, if it is a continuous time system, and they can be applied on x of kt, which is sample data system, which has got sequence of values at discrete instance of time. And this can also be, Z transforms can also be applied on x of k, which is nothing but sequence of numbers. That is, Z transform Z, capital Z, is of x of t, can also be represented as capital Z of x of kt, which is nothing but, the definition gives us sigma k is equal to 0 to infinity x of kt z power minus k, x of kt z power minus k, or Z transform of x of k is nothing but sigma k is equal to 0 to infinity x of k z power minus k. So you can see this by definition, Z transform of x of t is equal to Z transform of x of kt, which is equal to k, sigma k is from 0 to infinity x of kt z power minus k, and similarly Z transform x of k, which is sequence of numbers, which is equal to sigma k is from 0 to infinity x of k z power minus k. Now these are the basic, these are one-sided Z transforms. These are one-sided Z transforms. One-sided Z transforms where we are not having any value of x of t. We are not having any value of x of t for all values t less than 0. That is, x of t is equal to 0 for all t less than 0. From t is equal to 0 and above 0, x of t exists. Beyond the before or below the value of time t is equal to 0, the values of x of t does not exist. That is why it is called as one-sided Z transforms. Similarly, for x of k is equal to 0 for all k less than 0. Okay, so these are one-sided Z transforms. Now when you are going for a two-sided Z transform, a two-sided Z transform can be represented as Z transform of x of t is equal to Z transform of x of kt is equal to sigma k is from minus infinity to infinity x of kt z power minus k. Or similarly, Z transform of x of k is equal to Z transform of x of is equal to sigma k is from minus infinity to infinity x of k z power minus k, where k is from 0 is plus or minus 1 plus or minus 2 and so on up to plus or minus infinity. So these are a two-sided Z transforms. Two-sided Z transforms. So when you are representing any continuous time signal, or when you are representing any sample data signal, or you are representing any sequence of numbers in terms of Z transform, then you can call that as capital X of Z. You can also call this as capital X of Z, where X of Z is the Z transform of X of t. X of Z, capital X of Z is the Z transform of X of Z, where Z indicates the Z transform of Z represents the Z transform of X of t, where you will get X of Z, capital X of Z, which is nothing but sigma k is 0 to infinity x of kt z power minus k in the one-sided Z transforms, and in the two-sided Z transforms x of k, Z transform x of k is sigma k is from minus infinity to infinity x of k z power minus k. Now with this, if I try to elaborate this Z transforms, if I try to elaborate this Z transforms, if I am elaborating this one, what do I get here? X of Z is equal to, when I substitute k is equal to 0, I get x of 0 z power minus 0 plus x of 1 z power minus 1, x of 2 z power minus 2 plus 3 z power minus 3 plus so on up to infinity. Now this is our one-sided Z transform, a one-sided Z transform. Now when I go for a two-sided Z transform, what do we get? X of Z is equal to, it is from minus infinity, I am getting it here as x of, for example, x of minus 2z square plus x of minus 1z plus x of 0 plus x of 1z power minus 1 plus x of 2z power minus 2 plus so on. As you can see in both these cases, in the one-sided Z transform and the two-sided Z transform, you can see that in the one-sided Z transform you have all powers of Z, all negative powers of Z. In the two-sided Z transform, you can see that you are having z square, z power minus 1, z power minus 2, etc. Therefore, you are having both positive and negative powers of Z. Now, in our next lectures, we will be considering only one-sided Z transform. That is our limitation. We will go for with only one-sided Z transform, and hence we will be representing only x of z when you are considering, when we are discussing the Z transform of any function x of k or x of t or x of kt. We will be representing this equation, sigma k is equal to 0 to infinity x of k or x of kt z power minus k. Now with this, we will try to discuss some Z transforms of some elementary functions. Z transforms of elementary functions. first thing you will go for a unit step function. Unit step function. Now what is a unit step function? We all know that it is u of t, unit step function, which is equal to 1 for all t greater than or equal to 0, and you can also say that this is our function u of t, and from time t is equal to 0 the value is unit step function, it is 1. Now what is the z transform of u of t? Z transform of u of t, z transform of u of t is nothing but capital U of z, which is equal to sigma k is from 0 to infinity. By definition you can say u of kt, or u of t can be represented as u of kt into z power minus k. Now if I represent this, substitute values of k from 0 to infinity, I will have values from u of 0, z power 0, or z power minus 0 is 1, and u of 1 z power minus 1, u of 2 z power minus 2, plus so on. And since u of 0, u of 1, u of 2, etc. are all equal to 1s in a unit step function, then you will have this value as 1 plus z power minus 1 plus z power minus 2 plus so on. Now if you combine all these things and converge this entire set of equations, you will get 1 by 1 minus z power minus 1, right, and this can be represented as z by z minus 1. So this is the, what is the unit z transform of unit step function? You will have u of z is equal to z by z minus 1. This is your z transform of unit step function. Now in a similar way we will go for unit ramp function. We will go for unit ramp function, which is our second equation, and we know that r of t is a ramp function, which is nothing but t for all t greater than or equal to 0 and is equal to 0 for all t less than 0. Since we are going for only one-sided z transform, you are going for unit ramp function of this sort, and t 0 r of t, you can have this value is going from 0 to, from above 0 it is got value of t. R of t is equal to t for all t greater than or equal to 0. For this function, what is the z transform you are trying to find out? Then z transform of r of t, which is equal to r of z, which is nothing but sigma as k from 0 to infinity r of kt z power minus k. Instead of r of t, you can conveniently use r of kt. In this case, this is a sample data signal, because z transforms are applied on sample data signals, right? Once the continuous time signal is applied to a sampler, you will get a function which is r of kt. Now with this, when I replace this k with 0 to infinity, I will have r of z is equal to r of 0 z power minus 0, it is 1. Therefore r of 1 z power minus 1, r of 2 z power minus 2 plus so on, which is nothing but r of 0. In this case, r of 0 is equal to 0, since r of 0 is equal to 0, and r of 1 is equal to t, and r of 2 is equal to 2t, because r of kt is equal to kt. and for k is equal to 0 and r of kt which is equal to kt, I can have a table here, and r of 0 for k is equal to 0, it is r of 0, it is 0, k is equal to 1, r of 1 it is t, r of 2 it is 2t, and so on, right, r of 2 and so on. Therefore I can have this function where it is 0 plus t z power minus 1 plus 2t z power minus 2 plus 3t z power minus 3 and so on. So I'll get t as common and z inverse as common into 1 plus 2z power minus 1 plus 3z power minus 2 plus 4z power minus 3 plus so on, where you will get, after converging this series in bracket, what you get is you will have 1 minus z inverse whole power square, right. So you get here t z inverse by z minus 1 by z whole square, or you can say tz by z minus 1 whole square. So the Laplace or the z transform of any unit ramp function, it is tz by z minus 1, or z is equal to tz by z minus 1 whole square. Now this is the z transform of unit ramp function. Now we'll go and have a look at the third function, which is the polynomial function. The third one, the polynomial function. A power k. Polynomial function. What is the z transform of a power k? By definition, we can consider sigma k is from 0 to infinity a power k z power minus k. When you are replacing k with from 0 to infinity, you will get 1 plus a z inverse plus a square z power minus 2 a cube z power minus 3 plus so on up to infinity. Now if you a z inverse is the factor here, by geometrical progression you can say 1 by 1 minus a z inverse, or you can say z by z minus a. Now this can also be considered as unit step function when a is equal to 1. When a is equal to 1, what is the function a power k? It is equal to 1, which can be considered as a unit step function u of t. For all time, for all values of, for all k is equal to 0, 1, 2, so on. Right. So you will be having this z transform of a power k, and when you are converting a is equal to 1 and you are replacing a with 1, then we get z transform of 1 power k is equal to z by z minus 1. Therefore, a power k or unit step function is a special case of any polynomial function, a polynomial function a power k. And similarly, we can go for an exponential function. Exponential function e power minus a kt. Now what is the z transform of e power minus a kt, or sigma k 0 to infinity? By definition you can write it as e power minus a kt z power minus k, or you can write 1 plus, when k is equal to 0, in both these cases it is 1 plus e power minus at z power minus 1 plus e power minus 2at z power minus 2 e power minus 3at z power minus 3 plus so on. Now when you are going for geometric progression here and you are trying to converge this series, you will get 1 minus e power minus at z power minus 1, or you will get z by z minus e power minus 8. So this is your exponential function. Similarly, you can go with the Laplace the z transform of any sinusoidal function. Z transform of a sinusoidal function sin omega t or sin omega kt, right? So a z transform of sin omega kt. Now for instance, sin omega kt, you can write it as e power j omega kt, which is nothing but e power j omega kt is equal to cos omega kt plus j sin omega kt, and e power minus j omega kt, you have cos omega kt minus j sin omega kt. Now when you want to get sin omega kt, you can write e power j omega kt minus e power minus j omega kt by 2j, and similarly cos omega kt is equal to e power j omega kt plus e power minus j omega kt by 2. So using these two equations, already we have discussed what is the z transform of e power minus at or akt. Therefore you can simplify these equations and you can get the z transform of sin omega kt or z transform of cos omega kt. So with this we have discussed what are the various z transforms of elementary functions.